All right, hi everyone. Welcome to our final talk before we get kicked out of the space. So as a quick reminder, we have to depart promptly at 3:30. But before then, we have the pleasure of a talk by Soledad Villar, who's going to be telling us about exact and approximate symmetries in machine learning. Thank you.
Can you hear now? Okay, good. Well, thank you very much for the invitation. And I'm not used to hearing the pronunciation of my last name like that. So very nice. So, okay, so I'm going to talk about the role of exact and approximate symmetries in machine learning models. I come from an applied math department, but I collaborate with people in astrophysics. Please ask questions or comments, make comments if you have, if you want. So, so maybe some of you have seen this plot before. This double descent plot before. This is from a very influential paper in machine learning theory in 2019. Basically, what they show, Belkin and collaborators show that when you consider machine learning models, the classical statistical regime considers a setting where like you have typically much fewer parameters than data points, and then you can look at the expressive power of your class of functions, and the more expressive you are, the more you can fit your data, but also the more then you can overfit your data, and therefore you get like this behavior where like, well, maybe the best model is not the most expressive, but something in the middle that minimizes the bias plus the variance, the bias variance trade-off. But they show that in the modern machine learning regimes, actually what happens is like when you go beyond this like interpolation regime and you add more and more parameters and you make your class of functions more and more expressive, there is some form of implicit regularization that make that very flexible models can not only fit your training data perfectly, but also generalize well outside your training set. And this is kind of like the paradigm that people are using today in deep learning. They are using very flexible models with way more parameters and data points than training data points, and then just feeding their data perfectly. So one issue of having very over-parameterized models and having many functions in your hypothesis class that can fit the data perfectly is the question of how do you choose the right one? How do you choose a class of functions that works well? Meaning that when you do some gradient descent or some local method, you converge to something that has the correct inductive bias, meaning that it also generalizes well outside the training set. And so one of the claims that has been around recently is the fact that one of the design choices that is useful for giving you a good inductive bias have to do with expressing models that are consistent with the structure of the data that you wanna fit and the problems that you wanna solve. And most of these times, these models obey certain symmetries. So for instance, convolutional neural networks are translation equivariant. Recurrent neural networks use some form of time translation symmetry in text, and graph neural networks use some form of they are designed so they satisfy some form of permutation symmetry, and I'm going to talk more about that. And transformers also are designed to be very flexible and also implement many symmetries, like if, for instance, they're permutation equivariant if you don't consider position encodings, for instance. And this is kind of like the theme that people use in the topics of geometric deep learning, or like they want to design machine learning models that are applicable to the data that they use. So manifolds, graphs, etc. Depending on what kind of data you're looking for, then you want to express the problems. And in physics, that's something that shows up a lot. And in physics, symmetries play a fundamental role. And in the physical literature, there exist two kinds of symmetries that people distinguish. One is the active symmetries, the symmetries that are related to conservation laws. and that have to do with like observed regularities of the physics. And there's also the passive symmetries that have to do with the fact that when you take some problem and you write the problem mathematically, there's not a unique choice for this mathematical representation. So for instance, you can choose a different coordinate system, you can choose a different unit system, and then this change of coordinates and this change of units come with a symmetry, which is like the symmetry corresponding to do a transformation in my input, and then how does the output will transform in that sense. So two types of symmetries, passive symmetries and active symmetries. And the claim is that the machine learning models that should obey these symmetries, and that would improve their performance. And that's the claim that I want to make. And so how do you make machine learning models to satisfy symmetries? You can think of it in terms of group actions. So if I have a group that you can think of rotations, translations, scalings, groups that act on my input data, then I say that a function is invariant if every time that I do a group transformation to my input, my prediction doesn't change. That's group invariance. And I say that it's equivariant if I do every time that I do a transformation in my input, then the output is transformed by a predictable function of the group elements. So typically you write it as these commutative diagrams. Like if I do a transformation to my input and then I make the prediction, is the same as doing the prediction and then transform the predicted value. So for instance, in this pendulum example, I have, this is like just a double pendulum with springs, just a toy example. If I do a rotation in the XY plane, then of the initial positions and velocities, then the dynamics would be will rotate as well. So that's one symmetry. And in this particle system, if I make the prediction of the positions and velocities of this point cloud, then that if I do a rotation to all my positions and velocities, then the prediction should rotate as well. And so in equivariant machine learning, what people do is they parameterize the class of functions so that for any choice of parameters, theta that you can have, that you are learning, you have that the functions satisfy the symmetries. And so that's one way people implement this. So as an example, graph neural networks are designed to be equivariant. They also satisfy symmetries. And the idea is that if I have a graph, this graph has two things. It has the adjacency matrix and it has node features, which are the colors of the nodes in the graph. So when I represent this graph as an adjacency matrix, the representation is not unique. I can represent it like this, or I can permute, like change the order of these nodes and then represent it like that. So there's a group, which is a group of permutations that act in the graph by permuting rows and columns and by permuting node features. And then the claim is that if I'm going to do machine learning on graphs, then I need to be consistent with the symmetries. And this is what graph neural networks do. They are designed so they are consistent with the symmetry. And I'm going to talk more about graph neural networks. And yeah. So that's one example. So in this talk, I'm going to discuss, maybe not all of these, but some of these ideas. How do you think of equivariant functions in terms of invariant functions? How do you implement certain equivariant functions as well with respect to classical groups that show up in physics problems like rotations or orthogonal transformations or Lorentz transformations, and also how to use these ideas to get applications to contrastive learning, and yeah. And then an example of an application of invariant functions on point clouds in cosmology. And maybe I'll discuss more about graph neural networks in the end. But before that, I want to show you how people implement symmetries in practice. And so in practice, people do it via data augmentation, which doesn't really impose the symmetries, but it's just a way to like make your models to maybe be more consistent with the symmetries by transforming the input data in that way. And then, but for exact symmetries, what people use are representation theory, and I'm going to explain you how you can use representation theory to parameterize the space of equivariant functions. And then group convolutions or weight sharing, which is similar to what people do for graphical networks, and then invariant theory, which is something that I'm going to discuss later. So, okay, so representation theory. So how do people use representation theory to parameterize the space of functions? So the idea is the following. So you know the feed-forward, classical feed-forward neural networks are the compositions of linear layers and nonlinear activation functions, right? So you have like a linear layer, and then you have a nonlinear activation function that could be ReLU, for instance, the linear layer, etc. And so what one way of transforming this classical simple architecture into an equivariant architecture is by replacing the linear layers by linear equivariant functions. So linear functions that satisfy that every time that you do a group transformation to your input, the output transforms in the same way. However, this, and then you need to see, well, how can you do, what do you need to do to the activation function so that you don't break the symmetry with that. So the issue with this implementation is that sometimes just limiting the linear functions to satisfy this property is too much, it's too limiting. So maybe you don't have enough functions that satisfies that. So then what people do is they work in tensor space. So instead of considering just like your input space, they tensorize the space like k times, and then they look at the linear functions that take k tensors and output k tensors. And so this is kind of thinking about, instead of looking at the linear functions that are equivariant, it's kind of thinking as the polynomials of degree k that are equivariant. And so with that, they get a more expressive class of functions. But then the question is, how do you parameterize these more expressive class of functions? And they use representation theory. They use Schur's lemma. The idea is that they take this space, they decompose it in irreducible representations by computing the Clebsch-Gordon coefficients, and then they use Schur's lemma to understand which ones are the equivariant functions from that. That is complicated to implement in practice, but it is implemented in practice, and there are some packages that do that. There's the E3NN implemented by Tess Smith from MIT, and there's also a package implemented by people at Google that they do implement these equivariant methods using these irreducible representations for SO3. But in general, it's not really obvious on how to do it that way. So a simpler way that doesn't always work, but works for like SO3 and O3 and the Lorentz group, is instead of using the representation theory approach, where you just like change the linear layers to satisfy the symmetries, you can use the invariant theory to just understand how can you express the invariant functions, and then use that to implement the equivariant functions. So the idea is the following. So say that you have this point cloud over here, and you just want to predict the energy of this point cloud. So the energy of this point cloud is an O3 invariant function. So if I rotate all my positions, rotate or reflect all my positions and velocities, then the energy of this point cloud doesn't change. So mathematically, you can write it as like for any R in OD, like if I apply this R to all my input vectors, the function doesn't change. And so the first fundamental theorem for invariant theory for OD tells you that a function is OD invariant if and only if you can write it as a function of the inner products of the input vectors. So that tells you that any invariant function can be written in terms of the inner products of the input vectors. So you can compute the inner products of the input vectors, and any function that you obtain would be invariant, and vice versa. Okay. And then that is for the OD, which is rotations and reflections, but similar things can be, a similar characterization exists for other groups, like the group of rotations, SOD, then it would be like the inner products, and then you would get some determinants that come from the fact that SOD are the like the orthogonal matrices that have determinant equal to 1. So then the determinants need to show up in the set of invariants. And then, for instance, for the Lorentz group, which is a group that shows up in special relativity, you can write it in terms of the Minkowski inner products, which are the inner products that if you have like vectors considering like one time component and 3 or whatever, how many space components, then the inner product between this and that is going to be equal to the time components, the product of the time components minus the inner product of the space components. And then you have this other inner product, and any invariant function can be written in terms of these inner products. So then that suggests one parametrization of the space of invariant functions with respect to these actions. So that's for invariant functions. So now say that instead of just wanting an invariant function, I want to predict something that is equivariant. So I want to predict the position and velocities of all my particles in my system. So then I have my particle system, and then I'm predicting some function in RD, which I can be like predicting one function per point. So I'm many functions of this form, but I'm just going to tell you how to write one. But then you can do that for all of them, which is equivariant. So if I do a transformation to my inputs, then the output is transformed by that group element. So the theorem says that if you have a function that takes n vectors in Rd and outputs a vector in Rd, this function is OD equivariant if and only if you can write it as an inner product of, as a linear combination of my input vectors, where the coefficient functions are functions of the inner products. So they're invariant scalar functions. That is true for OD. It's not true for SOD. Like if you think of rotations, it's not true that you can write any rotation equivariant function as a function of as a linear combination of your inputs, because you can think of in the sphere, you can take two vectors and then the cross product, which is like the normal direction, that is also equivariant with respect to SOD, but it's not in the span of the vectors, okay? But you can generalize this result. So just saying that there is a way to go from the invariant functions to the equivariant functions, which is like a simple mathematical derivation. And if you're interested, I can show you what is the mathematical derivation. But if you're not interested, I can move on. Okay. Huh? You can vote. You can vote. Yeah.
All right. Who's interested?
Okay, I can show that offline. But the idea is that there is like a way to transform like if you have a function a function that goes from like B to W that is equivariant, then you can write a function that goes from B times the dual of W to R that is invariant. And there's like kind of like a way to go from equivariant maps to invariant maps and vice versa. And then that allows you to write like an algorithm to construct the equivariant functions. Okay, so I'm going to show you like one toy example, and then I'm going to show you an example that is not a toy, so that you believe me that this makes sense. But just as a toy example, just to understand how this model works, is the following. So I show you this double pendulum with springs that I had at the beginning. And so this is a Hamiltonian system, just I want to predict the dynamics. So there's many symmetries here. This is the symmetry in the plane that I told you earlier. But if you add the gravity as an input to your learning problem, then the function is not just like it's not just SO2, but it's O3 equivariant. Because if you rotate with the gravity with everything else, then the predictions of the pendulum would rotate. And so that's like a passive O3 equivariant symmetry, because it's kind of like a way of thinking is like there's a coordinate transformation that moved the gravity with everything else, and that's what makes it to be O3 equivariant as well. And so there's many symmetries. This is a Hamiltonian system. So there's a time translation symmetry that comes from the fact that the Hamiltonian is constant. And so we want to learn the dynamics. And the approaches that you can think of are like the classical, or like the simple way to do it is by using a neural ODE. A neural ODE is just like you parameterize a differential equation, and then you have a differential equation that you learn from data. You integrate that differential equation using like a solver, like a ODE solver, and then you compare the predictions that you get from this differential equation with the data, and then you take a gradient step, and then you update the parameters of the differential equation. That is the neural ODE model. And then what I'm saying is that this differential equation needs to be written in terms that are equivariant with respect to O3. And so then this differential equation would be parameterized with something that you take your input vectors, you compute the scalars, and then you learn the coefficient functions from the parameterization that I gave you earlier. So that is the way of writing this like neural ODE in an equivariant way. However, we can also use the fact that this system is Hamiltonian. And so we can, instead of learning any differential equation, you learn a Hamiltonian, and then you use a symplectic integrator to integrate the dynamics. And that would give you an extra symmetry, the Hamiltonian symmetry. And this Hamiltonian is going to be just a scalar invariant function that you can learn from data. And we can show numerically that the more symmetries that you impose, the better the performance of the prediction, right? Which is consistent with what the theory will say. So yeah. Another extension that you can do is like use the fact that, well, the Hamiltonian that I'm learning has units, which is units of energy, kilogram meter squared divided by second square. So I can make my learning of my Hamiltonian to be consistent with the units of the problem, which is another symmetry that you can impose. And then that you can do that using classical dimensional analysis. And you can parameterize the space of functions in that way as well. Okay, so I'm gonna show you a not so toy example of how you can use the symmetries to do other machine learning problems. So in this example, I'm considering the contrastive learning setting, where the idea is that I'm trying to learn an embedding for images. So each image is going to be represented in as a vector in the sphere. And so I want this embedding that I learned to capture information about the images, so I can use that embedding for like another downstream task that I want to solve. So the way people do this in contrastive learning is the following. They take an image, this cat, and then they consider different augmentations of this cat. So maybe this cat is like a more yellow version of this cat. They consider a set of augmentations for these images. And then they learn an embedding so that it's invariant with respect to augmentations. So all the augmented versions of the cat go to the same point in the sphere. And then the contrastive part comes from if I have another object like a dog, then the embedding needs to learn something that separates cats from dogs. So that's the contrastive part. And so there's this info-NCE loss, which is the loss that people use to learn these embeddings. So what we can do is we can use what I just told you earlier about how do you parameterize the equivariant functions on point clouds to understand how we can get some interpretable structure in this latent space. So the idea that I want to do is I want to find an embedding F so that when I apply the embedding of a cat and then augment this cat, then the resulting embeddings are going to be a small rotation of the other one. So that if I take a dog and then I take the embedding of the dog, I know what point in the embedding space corresponds to the same augmentation of that dog, because I know what rotation it comes from. You know what I mean? So I want it to be equivariant. I want this embedding to be equivariant with respect to rotations in the sphere. So like the embedding of the augmented cat is the same as a rotation of the embedding of the cat. That's the equivariance that I want. So how do you do that? Well, we can use the property that we had before, that we know that like if I have 2 points, y1 and y2, and 2 points z1 and z2, there exists an orthogonal transformation that sends this pair to this pair, even only if the inner product is conserved. Like if and only if they have the same inner product. And so using that, we can define a loss function, which is in terms of these inner products, that is also in terms of pairs, like the original sim-clear loss, that says that, well, what I want is that the inner products of the embeddings of the augmented different objects is the same as the inner product of the embeddings of the original objects. And if that's the case, if this is satisfied for all like fixed embeddings, say making it yellow, if that is satisfied for all pairs of points, then we know that there exists an orthogonal transformation, so that applying the augmentation corresponds to making the orthogonal transformation in the embedding space. And that gives you some interpretability of how can you work in this embedding space. These augmentations correspond to rotations. And then, yeah, so what we can do is we can define this loss function using this, like adding this loss term to the original Sinclair loss function. And then we can prove that, yeah, if you make this equivariant loss term equal to 0, then for any augmentation, for almost all augmentations, there exists an orthogonal transformation that make that happen. And if you can make that happen, which is, then if you interpret that your set of augmentations they're not a group, but if they were a group, then you could think that there exists a group homomorphism from like the space of augmentations to the orthogonal group. So you can think of your space of augmentations or whatever is not killed by this embedding to be like a subgroup of the orthogonal group. Yes.
Just on the previous slide.
Mm-hmm.
On the previous slide, so, but there's no guarantee that that's not just like the identity matrix.
Exactly. Yeah. That's excellent point. Yes, there's no guarantee that that's not the identity matrix. Yeah. So actually, we don't know how to prove that that's the case, but we observe that that is not the identity matrix in our experiments. But yeah, that's a great point. And so we believe, but we don't know that the reason why what you obtain is not the identity matrix is because the original Sinclair loss has a uniform term loss that makes everything spread out. So we believe that that's why it doesn't collapse the augmentations. But yeah, that's a great point. And also we don't have any explicit handle on like what orthogonal transformation it corresponds to, which is something that, I mean, you can get it from the data, but yeah. This, for instance, this example will show that the orthogonal transformation that we're getting is not the identity, because if we take this image and we do this augmentation and then we look at the nearest neighbor in the embedding space, then you see that all the nearest neighbors are yellow, so it captures the color. Whereas in the original Sinclair, it doesn't really capture the color because it's invariant with respect to that. So this kind of suggests that it is learning a non-trivial orthogonal transformation. But yeah, I mean, also you can also do experiments to get what orthogonal transformation you get. But yeah, that's a good point. Okay. So any other questions or comments? Mm-hmm. Yeah.
Just looking at your examples there between the two, is it exactly the suggestions you want? Because surely if you want to looking at the Sinclair versus Kerr outputs, I'd be more tempted to expect the output on the right than the ones from care.
Agree.
I have the image.
Yeah, it depends on what your task is, but you also can always get like you can see how much how much of the equivariant loss you want, and typically you want like a little bit of equivariance, but not a lot. Like you don't want this term to dominate the loss, because yeah, the invariant part is important, and the existence of the orthogonal transformation doesn't tell you that the orthogonal transformation is bounded in any way. So you want it to be close to the identity as well. Yeah. Okay. So so this is for orthogonal transformations, and the next thing that I wanted to discuss is an example of orthogonal transformations plus permutation symmetry that comes from a problem in cosmology. So I'm not an expert on, so it's kind of, I'm not an expert in astrophysics or cosmology, but I have collaborators like Kate Story-Fisher, who was a student of David Hogg at NYU, and we worked on this project together, and I come from the math side, so bear with me. But basically what Kate was working on was, she was working from data from cosmological simulations, and she wanted to infer certain properties of halos from the dark matter only simulations to the hydrodynamic simulations. So she wanted to kind of like identify how can you make some form of regression that would tell you like how do you infer the parameters here from whatever you have in the dark matter simulation. And so this regression problem is by nature like an invariant functions of these point clouds, because you can think of these point clouds as something that, first of all the points are exchangeable. So there's like a permutation symmetry, and also the orientation of the point cloud doesn't really matter that much. So it's also rotation invariant. So we have this like OD plus permutation symmetry. And the question is, how can we implement invariant functions on this? Like, how can we make a regression from the properties from here to infer the properties there, so that the model satisfies the symmetries of the problem? Okay, so we can use the same mathematical ideas that we had before. So now we can think of our data X, which is point clouds. It's a point cloud, so it's like n points in dimension D. And you can represent it as a matrix in D times n. And so in this X, you have the action of the orthogonal group on the left, and the action of the permutation group on the right. Like the action of the orthogonal group would be just like rotating the entire point cloud together, and the action of Sn would be interchanging points in this point cloud. Like the order of the points is irrelevant. So this is how you would write it. And so we know from what we discussed before with the invariant functions, all the invariant functions, is that a function is invariant with respect to this part of the group action, if and only if it's a function of the Gram matrix, right? Like the matrix of inner products. That was the first thing that we discussed. And now if we want to also take into consideration the Sn action, when you look at the matrix of inner products, the permutation of the points now is permutations of rows and columns of this matrix of inner products. So we kind of recover the symmetries of the graph inner networks, right? Like this, here we have permutation of rows and columns on the matrix of Gram matrices. So this is like very nice, but in practice, this is not useful, because we don't want to construct this very big matrix from the point clouds that Kate has, because this is ridiculous. It's like n squared. And so what we can do is we can use some certain features, and then we can prove that actually these features are sufficient to express almost all point clouds. And the features come from the idea that, okay, so given the action of the permutations on matrices, you have like two orbits. You can take any two diagonal elements and exchange them, and you can take any two of diagonal elements and exchange them, but you cannot exchange them independently. There's something that you have to do it so that it's consistent, like the exchanging of the diagonal and the off diagonal. And so you can write it as like the symmetry group. You can write it as like inside a bigger symmetry group, which is exchanging the diagonals and the off diagonals. And then you can use some techniques from Galois theory that tells you how can you write the field of invariant functions in this space. And using that and other ideas, you can reduce this construction to like n times d generators instead of like using the entire matrix. So you can write like a generators of the space of invariant functions using like n times d things and not like n squared, which is something that makes more sense for this problem. Okay. Okay, so I'm not gonna go into more details for that, but I'm happy to discuss it if you're interested later. Okay, so finally, I'm going to talk about graph neural networks, which is related to the things that we were discussing before. So graph neural networks are defined to be to parameterize functions on graphs. And so the idea is that if I have a graph, the simplest way that one can parameterize invariant or equivariant functions on graphs is by just looking at the local neighborhoods of each node. So if I have this node here, B, I can write equivariant functions by just looking at the neighbors of B, and then just like having a message function that each neighbor sends to B, and then having an aggregation function where like B aggregates all the information that it gets from their neighbors. That doesn't see the GCC matrix, and it's kind of like the simplest way of like parameterizing functions to satisfy the symmetries. Just like look at the local neighborhoods, have a function of that you send to your neighbors, and then aggregate those functions, and that is the basis of like this message passing neural networks. And also this is equivalent to certain forms of graph convolutional networks that basically just do that. However, this has a disadvantage that if you implement it in this way that is just like vanilla message passing with no extra thought, then what happens is that this architecture is not very expressive. Like there's many functions that you cannot express by just looking at the properties of your local neighborhood. For instance, if you take a graph that has these two triangles and a graph that has this hexagon, that is just this hexagon, these two graphs locally look exactly the same because every node has a neighbor that has two nodes. That has two neighbors, and each one has two nodes, and that's it. So using this message passing idea is not sufficient to distinguish classes of graphs that are very, very different. And so people have discussed many ways to extend these architectures so that they are actually more expressive and they're more useful for problems. But yeah, but just like the simplest, this message passing would not cut it. And that's something that may make sense to take into consideration if you're using just graph neural networks for any problem. Because sure, you want your graph neural networks to have the property that if you have two versions of the same graph, then it gives you a different value, a different function. Sorry, it doesn't give. Sorry, you want to have the property that if you have two versions of the same graph, the function is the same. But also you want to be able to separate graphs that are different, and that's not something that you always can do because that's the graph isomorphism problem, which is hard. Like we don't expect to solve it. So yeah, so that's for graph neural networks. However, the claim is that you don't always, not always that you have a graph, you need to use a graph neural network. And for instance, in this project led by my student Teresa, what she was thinking of is a problem where like you have a fixed graph and then you have a signal that changes with time on top of each node of the graph. And the claim is that for problems like these, maybe using a graph neural network is not the best idea. And so in this example, for instance, she has like, these are like highways in LA, and for each node in the graph, they know how many cars per minute you have at each location, and then the prediction task is to predict the how many cars you're going to have at a certain location, like will you have a traffic jam and things like that. And so here the graph is fixed, and there's like a time dependent signal on each node of the graph that you want to predict. And the claim is that the message passing architecture implements more symmetries than the problem has, and you may want to use something that doesn't implement so many symmetries to make it more expressive. And so the intuition here could be that in graph neural networks, you are permuting the domain and the signal together. Whereas in convolutional neural networks, you have like a translation symmetry that fixes the domain and then translates the signal, which is the image on top of a fixed domain, which is a grid, which you can think of it as a graph. So in convolutional neural networks, you kind of like decouple the action of the group from the domain to the signal. And then that's what she proposed for this problem. And actually, what she showed is that when you consider different classes of functions, so basically you can think of this plot over here. So this plot is indexed by the group of symmetries that you're implementing. So more symmetries imply smaller class of functions, because the more symmetries you impose, the smallest the class of functions that satisfy the symmetries is. So going in this direction, the class of functions become more expressive and the symmetry group becomes smaller. So you have like something like the double descent phenomenon that I showed you in the first slide. So the more, like here in this example, she showed that like the performance first improves and then declines when you make the class of functions more expressive, meaning that when you make the group of symmetries that you're imposing smaller. And that's some bias variance trade-off that you can think of in the case of this setting where like your graph is fixed, really. So you already know the identification of all the nodes with each other. So maybe that's a symmetry that you didn't need to impose from the beginning. And she can quantify this variance trade-off using some techniques that are not very complicated, like just statistics. And she can show that, for instance, you can impose more symmetries that the problem has, and then you can reduce the risk of your estimator by increasing the bias a little bit, but decreasing the variance significantly. And the way she would implement something like that is like if you have a graph, you can do clustering of the nodes of your graph, and then do just different message functions for different clusters in your graph, for instance. That could be one way of doing it. And yeah, and then she has some specific expression for a linear regression case, which you can compute the risk in closed form. And in her numerical experiments, you can see that in many cases, you actually obtain that the group that is optimal is something that is not the entire permutation group, but also not the trivial group. So it's something in the middle, which is like kind of like in the bias variance trade-off, but like in the regime, in the under-parametrized regime. Okay, so let me finish by saying that, well, I believe that maybe I convince you, but I don't know, that approximate symmetries or exact symmetries can give you a good inductive bias for machine learning, for the physical sciences in particular, and for engineering applications. And the tools that I discussed use invariant theory, representation theory, and we can rethink the roles of symmetries as model selection in the case of the graph problem. And yeah, that's it. These are my references.
Okay, do we have a few minutes for questions? Are there any questions from the audience?
If I were to try to make a, say, a prediction on an image, rotation invariant, I would have to represent this as the feature that would be the XY position on the image and the value the image takes. Let's say that's grayscale. Is that correct? And then there's all the inner products that have to be computed in order to represent a function or find a function of those of that extended gram matrix that represents whatever is the information content of images. Is that right?
Well, I wasn't discussing images here. I was just discussing like an n-body simulation. So every point has like positions and velocities. So in the image, are you thinking of like just rotating the image or like rotating something else?
No, I would like to have the information content of the image under the assumption that I can rotate it without changing that information content. That's similar to what Kate was doing, but it isn't just the positions, right? We have intensity at positions. So I wonder if the parameterization would then be 2 coordinates for positions and 1 for the value of the image at that location.
Yeah, you could do that, yeah. Okay. But the action would only apply to the position and velocity, and the intensity would remain constant.
Oh, I see what you mean. Yeah. Okay.
So this is more of an implementation detail question. When you, in your SimClear alternative, did you ever try it in the labeled case of having like triplet loss or something like that? And whether having the class labels there kind of remove the benefits you get from fixing your augmentations, because that might be more of a, in the loss function, that might be more of a sway than having the augmentations.
So what is it?
So triplet loss, instead of having just, here's an example with augmentations, this is the same versus anything else. You have, given an anchor, you have a positive and negative case in terms of class labels instead. I was wondering if you haven't tested it, you would expect to still have the benefits.
Yes, I think that you could also implement that, like you could have that in the loss function as well.
Yeah,
right? So you could have both. You can do that and you could do the equivariant loss, or you're saying replacing the equivariant loss by that. It's
just so by fixing your augmentations on your SimClear alternative, that's like, okay, this is giving us better performance, and it's having more impact on the embedded space. If you're then having the labels included with it, of this is a positive case of what we're looking at, and here's a specific negative case in terms of labels, do you think that is going to kind of dominate the how the embedded space is made, rather than you fixing the augmentations on both the positive and negative case?
Yeah, I think that would change the structure that you get in the embedding space, but I wouldn't know how. So I'm happy to chat offline. Yeah.
Go ahead.
Have you compared these types of symmetries embedded relative to quote unquote cheating when you say like, you know the symmetry in your data and you just translate your data in a preferred space in your symmetry and then just train it that way. Say you have galaxies that have ellipticity, just rotate all of them in the major axis.
Yeah, sure.
And just do it that way as an example.
Yeah, that if you have a way to choose the coordinate system so that, and then you do like kind of like a moving frame to that specific coordinate system, then the expressive power is equivalent. It's equivalent to do it by just fixing the axis mathematically. I don't know in practice, but mathematically it would be equivalent to do it that way, right?
Yeah,
but the thing is like you don't always know what is the way to align this. Like in the case of graphs, like if you have two graphs, what is like the canonical way of expressing this graph? What is the canonical ordering of the nodes? I mean, it would be something that you need to design beforehand. But in the case of the, if you have like these galaxies like that, and then you choose like this main axis, then yes, I think that would work.
So your recommendation is doing it that way, or is your recommendation choosing a symmetry?
So no, my recommendation, it depends on the problem. I will need to look at the problem and see what my recommendation would be. Yeah.
That's a nice talk. Soledad. I have a very practical question. Maybe this is too specific. So imagine that you have a graph, maybe representing, what you did with Kate, but you have several vector quantities for every node, let's say position and velocities. Maybe you have spins or something like that. How do you, in that case, construct the model to be rotational invariant? To construct all possible.
So in practice, what Kate did in practice was a little bit different from what what I mentioned. So what she did was like she computed moments of. So she had these point clouds, and then she did some binning of like say the main variance and like maybe one standard deviation, etc. And then she computed the eigenvectors of the covariance matrix at each of these layers, and these the eigenvalues are invariant with respect to all these things. So these are the features that she constructed in the problem that she solved in her thesis. Yeah, but I didn't. Yeah, but that I think that's what made sense for that specific problem that she was working on.
Any other questions? Okay, I have a quick one, if I can. So when you were talking about these like really nice sort of contrastive loss representations and wanting to have like a rotation group under which you expect the symmetry, you mentioned that the actual value of this lambda parameter was very important. Can you give me a sense of like what happens as you move that lambda parameter around? Like what happens if it's too small or too large in terms of like the types of representations or latent representations that you get out?
Yeah, so if the parameter is too small, then you just recover the Sinclair. So you're not able to distinguish between different augmented versions of your objects. And if the lambda is too small, then you know that there exists an orthogonal transformation. But what you want is that the orthogonal transformation to be like small in norm, because you still want that different augmented versions of your data points go to close by points. And if you don't have that, like if your lambda is too large, then you have no control on like how far these two things are. And if they're very far away, then you don't really have the structure that you want, I think.
Okay, any final questions before we wrap up? Okay, let's give her another round of applause for next one talk.